Okay, in this lecture, I will cover a topic which is actually quite important, although it's not very complicated, and it's that of transfer functions. To put it very simply, the transfer function is just the Laplace transform of the impulse response. So first, I'm going to briefly kind of recollect what the impulse response was and what we talked about during those lectures, and then I'll go through a few examples on to how to compute this transfer function. Okay, so like I said, like we said in the previous lectures, the transfer function, or h of t, is the solution to a circuit. Let's do an LC circuit, assuming that your input is a delta function. And what we said is, so here, let's say we're looking for IL. We said that what's interesting about the impulse response is that once you know the impulse response, if I want to know the solution to this circuit due to any input, so any, so let's say we solved this circuit and we got h of t, then for IL, then if we want to solve the circuit for any input, then we just simply have to take the h of t and convolve it with that input. So n's of t convolved. And that's going to give us our solution. So that was kind of the significance of the impulse response. And you've already been using this in your physics classes when you studied gravitation or electromagnetism. So in particular for electrostatics, what you got is that if you have a charge, its voltage or potential is equal to that charge divided by the Green's function, which is a sort of impulse response for the Laplace operator in 3 dimensions. And so then basically here what you're actually doing is a spatial convolution in 3 variables, the x, y, and z coordinates. In our circuits, we're only doing them in the time domain. All right, so that's basically a review of our previous lecture. And the reason I'm introducing this is because the transfer function is the Laplace transform of the impulse response. Now you might be wondering, why do we care about this transfer function, and why, if we already know what the impulse response is, what does having a transfer function buys us? And so in particular, what is bought to us has to do with the fact that whenever we have any input, we have to convolve with that input. So let's look at convolution in the Laplace domain. And we've already kind of gone over this in previous slides, but what we found is that the Laplace transform of the convolution of 2 functions is actually the product of those 2 functions. So what that means is that if I want to do a convolution between my input and h of t, in the Laplace domain, that corresponds to just taking the product of my input with the transfer function. And so as a result, this will be actually much more efficient. Okay, so what is the transfer function? So there's 2 ways to define the transfer function. One way is to say, well, if I have an input x of t, and an out, and my h of t is my impulse response, then I know that the Laplace transform of the convolution will be the output. And so in the Laplace domain, that's the equivalent expression. And so I can say that the transfer function is just the ratio of the output to the input. In the Laplace domain. So that's one way to see it. Another way to see it is just to say, well, if I assume my x of t, or my input, is a deltas of t, then I'm going to have some circuit elements here. Then that means that in the Laplace domain, because the Laplace transform of a delta function is 1, this circuit will basically, that input will become a 1. So it's just the solution to the circuit when I assume that my circuit has 1 as its Laplace transform source. Now note that this is completely compatible to this, because if I choose the input as 1, then y sub s would be that ratio to the input to the output. So you can think about it two ways. One is you put 1 as your input, because that's the Laplace transform of a delta function. Or you can think about it as we're trying to find the ratio of the output to the input. Okay, so that's basically all you need to know about transfer functions. Now I'm going to go over a few examples. Okay, let's look at an example. So here it's asking us to find the impulse response, but what we're going to do is we're first going to find the transfer function and then inverse Laplace it. So in particular, to find the transfer function, we're always going to assume 0 initial conditions. This capacitor gets replaced with an impedance of 1 over SC. And then we have that, so we have 0 initial conditions, and then we replace Vn with a 1. So I'm just going to redraw the circuit here, plus minus 1. And then we have R, and then we have 1 over SC. So I can just say here that I can use KVL to say that this is just really, oh, and then here we have VC. That 1 has to be equal to I times R, plus, and I is the current coming into the circuit, plus VCs of S. So remember, we want to solve for VCs of S. And because this is the current going through here, algebraically, that means that I equals VC over 1 over SC. So I is just SC times VC. So we can just write this as SC R times VCs of S plus VCs of S. And then we can factor out the VC and divide both sides so that we get that VCs of S equals 1 over SCR plus 1, which is going to give us that this is just 1 over CR divided by S plus 1 over CR. And then now we know we can just inverse Laplace this. So we're going to get that VCs of t equals, so this is the transfer function h of s, because it's the solution when we assume that the input is 1. And additionally, we can get the impulse response by taking the inverse Laplace, which is just going to be 1 over RC e to the negative t over RC u of t. And that's it. That's our impulse response for this circuit. Now, if you remember last time, before we used to have to solve for the unit step response and then take its derivative. Now it's much more straightforward if we do this in the Laplace domain. Okay, so here's kind of the solution. To solve this, I did kind of a trick where I just basically looked at the current going through here, going into this node. I look at KCL in this node, and so I have Vn minus Vc over R, which would be a current going this way. And then I subtract from it a current going that way. I add to it a current going that way, and they have to add up to 0. So that's this equation. And then with some algebra, I get the same result that I got in the previous slide. And then once I know my transfer function, I can take the inverse Laplace to get the time domain function. Okay, so that's basically all. I'm going to go through another example and then we can call it a day. Find the impulse response. Okay, we already did this. So I think I just wrote this here so that you would have the answer. Yeah, okay, so one thing to note before we move on from this example, let's say we assume Vn of s equals 1 over s squared, so meaning that the Vn of t is actually equal to t u of t. And now we want to know what the output is. And we're assuming that r times c equals 1. So we know that h of s equals 1 over rc s plus 1 over rc, which in this case would be 1 over s plus 1. And it's asking us what Vc of t is. So we could either do this, which would be kind of, we could either convolve h of t with t u of t, which would require us to solve for this integral, 1 over rc, the integral from negative infinity to infinity of e to the negative tau over rc, u of tau, and then times t minus tau, u of t minus tau d tau. I'm guessing a lot of you don't want to do this. Alternately, what we can do is just simply take the inverse Laplace of h of s times Vn of s, and those two things will be equal. And that's just equal to 1 over s squared, s plus 1. So as you can see why you would want to do this. So basically now what we would have to do is just find the three coefficients. So we set this equal to a1 over s plus a2 over s squared plus a3 over s plus 1. To find a3 would actually just be equal to 1 over negative 1 squared. So remember, you multiply both sides of the equation by s plus 1 and evaluate at the root, or negative 1. To find a2, we're going to have 1 over 0 plus 1. And so that's going to give us, this one's going to give us 1, this one's going to give us 1. And then to find a1, we actually have to evaluate this expression at 1. So I'm just going to go ahead and plug in here 1, 1. And then if we evaluate this whole expression at 1, we're going to get 1/2. So basically 1 squared is just 1. 1 plus 1 gives us 2, so it's 1/2. And then we're going to have that that's equal to a1 plus 1 over 1 squared plus 1 over 2. And so we will get that a1 is actually negative 1. So now we have a1, negative 1. And then we can actually find the time domain solution by simply looking this up in the tables. So we're going to have negative u of t plus t u of t plus e to the negative t. So we could have also solved this integral, and if you want, you can confirm it, and we would have gotten the same answer. But now we can do it much faster by using our Laplace transform. And here's kind of the same solution I got in the previous slide. So remember, we use our formula from, not lecture 22, so the inverse Laplace lecture. So these don't quite map to this is actually the book lecture 22. And the book lecture 22, not my lecture 22, basically. Yeah, so we just used kind of the method for inverse Laplace transforms that were given to us, and that allowed us to get the coefficient that multiplies the 1 plus s, and the coefficient that multiplies the s squared. And then once we find those two coefficients, we just evaluated at 1 to get the value of a2. And once we have an a2, then we just basically inverse Laplace everything. Okay, so that's basically how you can actually use these transfer functions, and you can already start to see how powerful this is because we didn't have to do any convolutions. So let's find the impulse response for this particular circuit, and let's just assume 0 initial conditions. So what that means is we have to solve this circuit, and remember when we're finding impulse responses, we can always assume 0 initial conditions, so this just becomes 1, and then in the Laplace domain, and then we're going to have 0.4s, and then we're going to have s over 0.05, which is, milli, 1, 2, 3, yeah, 1, 2, so 100 over 5, which is 20, the s should be down here, so 20 over s. So 5 over 100 is 20, so that's why we get 20 over s. Okay, so there should be a 1 here. So when we move it 2 on the top, we have to move it 2 on the bottom. So we move this 2 on the top, 2 on the bottom, 1, 2. So this is just 5 over 100. And then, yeah, so that gives us 20 over s. Okay, let's, now that we know that this is we want to find IL, so that means that ILs of s, which is h of s for this particular case, is just going to be 1 divided by the sum of the impedances, which is 0.4s, plus 20 over s. And then we want to get kind of a polynomial in the denominator, so we want to multiply by s and divide by 0.4. So we're going to get basically 1 over 0.4 s squared plus 20 over 0.4. And luckily we've done this circuit many times, so we know that 1 over 0.4, well, that's just 10 over 4, which is 2.5 s. And then 20 over 4 is just 200 over 4, which is just 50. And then finally, we can actually now, oh, and there should be an s square here. And so this one, we can actually look straight up from the Laplace tables. So we don't even have to do the partial fraction decomposition. You could, and you're going to get that the roots are real, so you're going to get the cosine, but here it is. And in this case, it's just going to be 2.5 cosine, and then omega naught squared, so square root of 50 t, u of t. There you go. That's the impulse response. So see how easy it was to get that? Yeah, so that's basically it. So we got the impulse response. In the previous case, we actually looked at this. So now we can see something interesting, which is that to find the solution due to this scenario, we just have to multiply by s plus 3. And so we're going to get that. And we already did this example. You know, I've been going over the same example because I don't want to waste a lot of class time doing inverse Laplace transforms. But basically, you see that this is the expression that we got when we solved this circuit in the previous case. So indeed, it does match what we had in our previous example. So here's the solution. So that's pretty much it. So in conclusion, the transfer function is the impulse response in the Laplace domain, and to solve it, there's two ways. You either find the ratio of the output, which we don't actually do today, to the input, or you can assume input is 1 in the Laplace domain or a delta function in the time domain. And then in that case, your output will be your transfer function. Yeah, so output will be transfer function. Okay, so I'll see you next time.